This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Can you hear me if I speak like this?
The microphones aren't working right, so you have to come close up. I know everyone's scared of the front, but...
It may be better if you're a little closer, and you might be able to see my writing a little more easily. So
Even the front row is
the front row is not taken.
lots of legroom, right? It's like business class.
Oh.
I think I have to take a photo. This is really inspiring.
All right. It seems as though we're not going to have microphones, so you should tell me if you can't hear. Please. I'll be terribly upset if I think you're not listening or hearing what I'm saying. And if you're not following, you should be asking a question. I expect you to be thinking about what I'm saying and asking questions if you don't understand it. There's nothing here that I'm going to talk about today that you don't understand or that you haven't seen before, more or less. So we got down to, and you'd have thought this thing was working, but it's not.
The scroll wheel?
The scroll wheel's not working.
You have to hold the cursor over the... Yep, and now try. Yeah.
I have to hold the cursor over what?
Just like the main page, really. See where the cursor is, right? If it goes off the paper,
All right.
it's no longer scrolling paper.
Okay. Well, last time we're just reviewing some basics, but we're going to need them very much in compressible gas dynamics. So we need an equation of state, and we need to know where that came from and what's related to it. So that's why I'm doing what I'm doing. So in this first equation, dq is dE plus pdV. The right-hand side are all variables of state. That's to say they depend only on specific conditions. There's a specific volume and a specific pressure because we're talking about a system that is in equilibrium, basically. And the internal energy depends only on the state of the system. And we'll come to that a little more. So the variables of state, but the left-hand side is not a variable state, that it is not a perfect differential whose change only depends on the initial and final states, whereas the internal energy is postulated to be a state variable to depend only on the initial condition and the final condition, and it's independent, therefore, of the path that you follow in a PV diagram. All right, so now let's talk about the second law of thermodynamics. And again, I can't emphasize how much these were controversial not so very long ago. Lord Kelvin stated it in the way that is most useful for proving things. He said that a transformation whose only final result is to transform into work heat extracted at a source which is at the same temperature throughout is impossible. That was Lord Kelvin. That's Lord Kelvin's statement of the second law. What I hope you may have seen previously is a proof that that's the same thing as Clausius' statement here, which is that a transformation whose only final result is to transfer heat from a body at a given temperature to a body at a higher temperature is impossible. That's Clausius. You can only transfer heat from a higher temperature to a lower temperature. So now we're going to talk about some things that follow from that, because we've got to talk about the entropy. And one of the really important ideas is the idea of a Carnot cycle, which I hope you've all seen and know what it is. But a Carnot cycle in a PV diagram is a cycle that starts here at A and is isothermal as you expand the volume from the volume at A to the volume at B. And then you expand again to a higher volume, and you expand in an adiabatic way. So here is Q equals 0. And now to make it a cycle, so this is at T2, and to make it a cycle, you go back, you now start to compress it, and as you compress it, the pressure typically rises if you keep the temperature constant. Beg your pardon? Oh, yeah. Good God. And so that's all done isothermally at one temperature, T1. And in order to do that, if you compressed it and increased the pressure, if you didn't take heat out of it, it would get hotter. So to do that isothermally, you've got to take heat out, and that's Q1. Here you've got to put heat in, that's Q2. And then finally, adiabatically, Q equals 0. You go from B to A. So that's a Carnot cycle. And one of the great results, we might say something about it, is that Q2 is absorbed at T2 and Q1 is rejected at the lower temperature T1. Then for any reversible cycle, any cycle like that, any reversible, that means you do it quasi-steadily. There are no currents, no heat, and so you have to go step by step infinitesimally. Q2 over Q1 is the same thing as I did it for a different engine. Between the same temperatures, I get the same answer. Q2 prime over Q1 prime, so that's a different cycle. And they're both, that ratio is a function only of T1 and T2. And because it's a cycle, you do work around the cycle. The PV, if you integrate PdV around this cycle, you get this area here. So that's the work done by the cycle. And because you start at A and you finish up at A, it means the internal energy, because it's a variable of state, you postulate that it's a variable of state, and you finish up at A, there's no change in the internal energy. So it means that the work done is exactly Q2 minus Q1. Yes, Q2 minus Q1 is the work done, and the heat that you supplied to this system is at Q2. This is burning coal, for example, if it was a steam cycle. Q2 minus Q1 is the amount of work done, because there's no change in internal energy. That's from the first law. So the work done by the amount of heat supplied is the efficiency. So all reversible engines, Carnot cycles, operating between the temperatures T2 and T1 have the same efficiency. Q2 over Q1, you can see that the efficiency is Q2 minus Q1 over Q2, which is 1 minus Q1 over Q2. So that's a function only of the two temperatures. And so they all have the same efficiency. And that's, in some ways, why the efficiency of those early Newcomen engine at 2.7% or something is so dramatic. We've come a long way since then. Right, so now we're going to talk about two engines, two Carnot engines, and we're going to reverse one of them, the first one here, the one on the left. But before we do that, we're going to say that one engine's a big engine and the other engine's a small engine. And so they don't do the same amount of work. They don't carry as much mass, and so they don't do the same amount of work. But we're going to suppose that the work done by the cycle is, of course, Q2 minus Q1 by the first law. And for the other cycle, it's Q2 prime minus Q1 prime, right? So we're going to suppose that Q2, that's the heat supplied to one engine, is very different from the heat supplied to the other engine. But we're going to say that that ratio is n prime over n. And we could make n arbitrarily large. And we could match Q2 over Q2 prime almost exactly. So if they were very close, one was 1501 and the other one was 1499. So it gets arbitrarily close as you make those numbers bigger. And now what we're going to do is we're going to take n prime cycles of the first engine, of the second engine, and n cycles of the first engine, but we're going to make the first engine go in reverse. So it's a reversible engine. It means we're going, instead of rejecting at Q1, we're going to supply at Q1 and we're going to reject at Q2, and we're going to go around the opposite way. And so the work done will be minus. You'll have to put work in. So we're going to take n prime cycles of the second and n cycles of the first, but in reverse for the first engine. So the total work done, if it's W per cycle and W prime per cycle, then the prime one is going in the direction that I've got here, and the other one's going in the opposite direction. So the work is plus W prime and minus W. And so the amount of work done, if I have n prime, take the prime one n times around and the other one n times around. And so now, how much heat is absorbed at T2? Well, Q2 prime is absorbed by the first engine, but Q2 is rejected by the first engine because it's going in reverse. So the amount of heat supplied is n prime Q2 prime minus n Q2. And you can see from this line above, Q2 prime, the way we set this up to be identically zero. So there's not going to be any net heat supplied from T2. So so the total heat absorbed by the engines will be n prime Q2 prime minus n Q2, which is the Q2 total, and that's going to be zero. Whereas the heat's given up at T1 is n prime Q1 prime, so we're rejecting heat from that prime engine and we're absorbing heat from T1 for the engine in reverse, and so that's minus nQ1. So the total work done is Q2 total, the total heat supplied minus the total rejected. And when you put that in, you get one minus the other there. But NQ2 from one engine is exactly equal and opposite to the heat rejected by the other. And so Q2 total equals naught. So that means that the work done must be the Q1 total, which is NQ1 minus N prime Q1 prime. And so now you can see that this is Kelvin's postulate here. So what Kelvin had to say is that you can't, the only consequence of this is to get work out of this system but it's all coming from one temperature. So that's the trick here, where we're doing what Kelvin wanted us to do. He wants to be able to show that this is impossible, unless you're not doing work by the system, you're doing work on the system, and you're not supplying heat, you're actually rejecting heat only. So Kelvin's statement of the second law says that this W total has to be less than zero. In other words, that N prime Q1 prime has to be greater than NQ1. And that means that if I just take that result there, N prime Q1 prime has got to be greater than NQ1, which means that N prime over N has got to be greater than or equal to Q1 over Q1 prime. And but right back at the beginning, we said what the ratio of N prime was. It was set up to be so that Q2 over Q2 prime was N prime over N. So Q2 over Q2 prime must be greater than Q1 over Q1 prime. Or, yes, Q2 over Q1 must be greater than Q2 prime over Q1 prime. Yes. Right. So now that's a very important basic idea from thermodynamics. And you can easily see that if I had said, well, both engines are reversible, if both engines were reversible, then it tells me that I have to have the equality, because I could make the exact argument where Q2 prime over Q1 prime was less than or equal to Q2 over Q1 by making the other one reversed and the other one in the same direction. So if they're both reversible, one has to be equal to the other. So that's a very important result. I just proved it for you. Way back there, I said that they had the same efficiency. All Carnot engines operating between the same temperature, two temperatures, have the same efficiency. So with both engines reversed, but with the second engine reversible, but with the second engine reversed, then I can deduce that Q2 over Q1 is equal to Q2 prime over Q1 prime, and that's a function only of T2 and T1. So that's a profound result, and we're going to use it. So now I want to introduce the idea of absolute temperature. So there's a theorem that I'm about to prove, which says that this function, T2 and T1, this is the ratio of Q2 over Q1, heat supplied over heat rejected. That's a function of T2 and T1. That's equal to the ratio of the same function of two other temperatures, T2 and T0, divided by the same functional form of T1 and T0. Now that's a theorem that I'm about to prove, but it's a very significant theorem, very significant idea. What's behind it? Well, we proceed. Let's suppose we have, as I've said here, one system, I've called it A1, which is a reversible Carnot cycle, and we supply heat Q1 at T1, and we reject Q0 at T0. And we have another reversible cycle, which supplies heat Q2 at T2, and Q naught is rejected at T naught. So it then follows from what we've said about this function. We've said it here. Q2 over Q1 is a function of the two temperatures. So if this is true, then Q1 over Q naught is a function of T1 and T naught, and Q2 over Q naught is another function of T2 and T naught. So now these two engines are going to be reversed, and so we're going to turn A and make it go backwards. So we're going to have to, it doesn't do work, we have to do work on it, right? A bit like a refrigeration system. So, and we're going to set this problem up so that there is no heat to or from T naught. So whatever A2 rejects at T naught, A1 is going to absorb at T naught. So there's nothing going to T naught. So that's just like a single system operating between T1 and T2. They're Carnot cycles. So we're reversing that, and we're saying that there's no heat to or from T naught for the composite cycle. So for this composite cycle now, so we're taking A1 is reversed, and so there's nothing at T naught. So A2 receives heat supplied at T2, and A1, which is going in reverse, now rejects heat at T1, rejects heat T1. So that's the same as a Carnot cycle. You're supplying heat at a fixed temperature, and then it's adiabatic on the sides. So it's exactly the same as a Carnot cycle. And so Q2 divided by Q1 from this, do I have a pointer that I can point to something on the blackboard?
I think we have one.
Ah, there we are, yes. In a perfect world, yes. Yeah. Thank you, Lloyd. So we can divide. No, this is going to die. The battery's died. All right. You can see now there's two top lines there. If I divide Q2 by Q1, because it's a Carnot cycle, it must be a function of T2 and T1, the two temperatures involved. So that's the function T2 and T1. But from the first line there, it's also equal to the function of T2, T naught divided by the function of T1 and T naught. Now, how could that be? You're all clever mathematicians. How could that possibly be? How could I have the ratio of two functions involving T naught and the same function on the left-hand side in which there's no T naught? How could that be? Come on, there must be someone here who recognizes instantly why that must be true. How could it be true? It must be that T naught is a multiplicative factor that cancels for the ratios. And so, otherwise you couldn't get rid of it. You couldn't get rid of T naught unless it was a multiplicative factor outside the function. So this thing has to be a function then. So T naught's a constant, or you think of it as T naught as a constant in this, in the right-hand side. So it's ultimately a function of T2 divided by a function of T1. And since T naught is not present on the left-hand side, so it has to cancel. Otherwise it's mathematically impossible. So that function of T2 and that function of T1 is called the absolute temperature. So theta is this function of temperature, and it's called the absolute temperature. Now I want to talk about, because we're going to say a lot about perfect gases. What's a perfect gas? Well, you all know, but it's certainly a perfect gas is defined, of course, by its temperature and its volume and its pressure and its mass. But the equation for a perfect gas, I hope you know, is P is nKT. Or if I where n is the number of particles in the volume, number per unit volume, K is Boltzmann's constant. So P is nKT. If I multiply the number of particles per unit volume by their mass, by the mass of each particle, so I take m, which is the mass of the particle, and multiply it by the number of particles in a unit volume, what do I get? I get the mass of one volume, of unit volume, which is the density. So another way to write that is mn is rho, and now I've got k over m, and that k is Boltzmann's constant divided by the mass of the particle is the gas constant for that particular gas, R. So P is nKT, P is rho RT, or since rho is the mass divided of some sort of mass in a volume divided by the volume, it's equal to m over v RT, or PV equals mRT. You would have had that at high school. And it's also written in a molar way, where the number of particles in the molecular weight is called Avogadro's number. And Avogadro's number, we'll come to it in a minute. So if I take this equation, P is nKT, and I divide n by the standard number of particles, Avogadro's number, and multiply it by n, and Kn, T, then I get n over n is the number of moles, which you would have heard from high school chemistry. That's the number of moles times R mole, where R mole is R times the molecular weight, times T. So P is equal to N R mole T. That's another way of writing the equation of state for a perfect gas. And R, as I said, was K over M, which is K times N, and that is where N is Avogadro's number, as I said, the number of molecules in the molecular weight, divided by Mn, and M is the mass times the number of molecules in the molecular weight, and I get the molecular weight. So Kn is R mole over the molecular weight, or R mole is equal to the molecular weight times R. And there's some numbers that I hope you will remember, that Avogadro's number is 6.02 times 10 to the 23, and the Boltzmann constant is 1.38 by 10 to the minus 23 joules per degree. So, and now to be in SI units, and joules are in SI units. To be in SI units, we want the mass to be, or the molecular weight to be in kilograms. And so the molecular weight in grams, like nitrogen, is 28. The molecular weight is 28, but in kilograms, it's 28 over 1,000. So you must remember to put that in. All right. And what are the units of RT? Well, they're a velocity squared, and let's just see if we can see why that. PV is equal to mRT, so the units for RT are PV over now what am I doing? Oh, yes. What I wrote down here is that the pressure is a force times an area. So the force is a mass times an acceleration. So there's an m times an L over t squared. And it's a force per unit area, so I've got to divide by L squared. And then, so that's the pressure, the units of the pressure, and then I've got to divide by the density to get RT, and the density is a mass over a length cubed. So you can see immediately that L squared in the denominator cancels with L to the fourth in the numerator, and so I got L squared over T squared. In other words, RT is a velocity squared. Now, let's just see something about this perfect gas. And so here's my cycle, and we're going from A to B to C to D. And it's going to be with a perfect gas. What I want to show you is why the absolute temperature is measured by a perfect gas thermometer. So why would that be true? So in going from A to B, we're going to say that the internal energy doesn't change. I'm going to say a bit more about the internal energy in a minute. That was a great result due to Joule. We'll come to it in a minute. But E is a function only of temperature. And we're going to say it's a perfect gas, so PV is mRT. So how much heat has to be supplied in going from A to B? Well, the heat that's supplied is the change in internal energy, EB minus EA, but they're at the same temperature. So they cancel. And plus the work done in going from A to B, that's P dV. So now, what is P? P is mRT over V, and T is at the temperature T2. So I've written there, and that, it's a pity I can't point to that darn thing. Can you see what I've done there? Anybody not follow what I'm doing? You have to follow what I'm trying to do. Otherwise, you'll spend days trying to unscramble all this. If you don't understand it now, you won't understand it later. That would help. Thank you, Tony. So, PdV, I'm substituting for V, mRT, and the temperature's fixed, so it's at T2, divided by V, and then I've got a dV, so I'm integrating from A to B, dV over V, which is log of VB minus the log of VA, so that's the log of VB over VA. So that's the heat supplied in going from A to B, and in going from C to D, I'm going to get the same thing. It's going to be VD over VC. Yes?
We can't replace T2 by T1 in
Q2? No, I need to keep the T2 in, because that's from A to B is on the top part of that, and that's isothermal by definition. All the heat, you have to supply heat. You're going to expand this volume, and the gas is going to get colder. So the only way to keep it at constant temperatures is to supply heat, right? So you're supplying heat Q2, and then you're going to reject heat minus Q1 and going from C to D, right? And it's going to be that. So the ratio of Q2 over Q1, and you have to understand that Q2 is supplied in this and Q1 is rejected. So it's T2 over T1. The M is the same mass and R's cancel, so it's T2 over T1, and it's the log of VB divided by VA divided by the log of VC divided by VD. Now, what about the expansions from B to C and then the compression from D to A? Those are done adiabatically. And if it's a reversible process, you do it very slowly. It's isentropic, as we'll see. And I haven't yet done it, but I'm going to in a little while. I'm going to tell you that for an isentropic process, PV to the gamma is the ratio of the specific heats, is a constant. Now that's not obvious, and we'll have to come to why we conclude that later today or tomorrow. All right. So if it is true that PV to the gamma is a constant, then I can write for P, and it's the same mass, the same gas constant, I can write PV is equal to MRT, so that's T, so that's P is going to be proportional to T divided by V. And so that says that T times V to the gamma divided by V, I mean, would be TV to the gamma minus 1, and that's going to be constant. So if it's an adiabatic process, TV to the gamma minus 1 is a constant. So that means in getting from C, finishing up at C here, and here's D, A, B, C, D. So this is isentropic here. And it's telling you that T, so if I take this constant to the power 1 over 1 divided by gamma minus 1, then I've got Tc to the 1 divided by gamma minus 1 times Vc will be equal to Tb 1 divided by gamma minus 1 times Vb. And equally, on the other side, I've got Td to the 1 divided by gamma minus 1 over Vd is Ta to the 1 over gamma minus 1 Va. So that I conclude from that, since Tc is equal to Td, the same temperature here as it is here, and the same temperature here, Ta is V, then it means, because these two things are isentropic starting at the same temperature, it means that the ratio of the volumes, Vc over Vd, is equal to Vb over Va. So that is why, way back up there, Q2 over Q1 is absolutely equal to T2 over T1. So isn't that remarkable? Here's a Carnot engine, and I can determine the ratio of the heats that I have to supply for this engine and reject T2 and T1. I can get those temperatures from a perfect gas thermometer. Remarkable. All I had to do was use a perfect gas, or imagine a perfect gas, as a thermometer. All right, so that's a proof of that. That's to say, Q2 over Q1 is T2 over T1, which I just proved, and that says that this absolute temperature that I called theta is actually the T of a perfect gas thermometer. All right. How many have all seen this before? How many have not? Nobody courageous enough to put... Okay, so you're familiar with all of that. Now, the next thing that follows is the remarkable idea of entropy. And my experience is that all of you have heard of it and none of you understand it. So I'm going to say something about it for you because we're going to say quite a lot about entropy in gas dynamics. So now, supposing, did you just put...
I tried really hard, but they didn't have one in the next theatre.
No, it's too good to be true. It's all right. It's all right. You have to look at what I'm doing up there. Don't look at me. Look at what I'm doing. Okay, so we've got an arbitrary reversible. So now we're going to talk about a reversible cycle. But it's an arbitrary cycle. So there it is on the left-hand side. There's P and there's V. And we're just going to go around that circle. That's the cycle that I want to work out. Now, what I'm going to do is I'm going to replace that cycle by an infinite number of Carnot cycles. I just drew one there. They're infinitesimal Carnot cycles. You can see that little one there that goes, it supplies dQt right up the top there. Imagines its constant temperature for a very short length of that cycle. And it supplies heat dQt, and then it rejects heat dQ1. And next door to that cycle is another one, and next door to that's another one, and the next door to that is another one. So do you see the picture? You've got a whole bunch. You replace that cycle by an infinite number of narrow, very, very narrow Carnot cycles. And the whole main cycle is reversible. So we're going to represent the actual cycle is the sum of an infinitely narrow Carnot cycles, of an infinite number of infinitely narrow Carnot cycles. And so because I, for this present, I don't want to get the signs confused, I'm just going to talk about the modulus of the sign, plus or minus. Heat supplied or heat rejected is just plus or minus. But the ratio that you've seen me just prove for the Carnot cycle, dQ2 over dQ1 is the ratio of the temperatures, T2 and T1, right? So what that says is dQ2 over T2 is equal to dQ1 over T1. That's this second to last line there. And if I'm taking the heat supplied as positive and the heat rejected as negative, then I'll have dQ2 is equal to minus dQ1 over T1. And so I can take it across, take the right-hand side to the left-hand side, and I get dQ2 over T2 plus dQ1 over T1 is equal to 0. That is an incredible result. It says, if this is a reversible cycle, and I can replace it all by Carnot cycles, that the sum of dQ over T is 0. Now, there's some amazing conclusions to be drawn from that. It says that around this loop, dQ reversible divided by T is equal to 0. That is, every contribution which is positive is also balanced by a negative, and they all cancel in pairs. They all cancel, contributions cancel in pairs. If all the dQs were supplied, now this is a separate idea, if all the dQs were supplied from reversible Carnot cycles, operating from a single source at T0, then once around the system cycle leads to the total heat supplied to the system only from the temperature T0. So that may be what you've seen in classes before. Only from the reservoir at T0. And since the heat supplied or rejected, dQ0 over T0 is T0 over T, dQ0 over T0 is dQ over T, then the total heat supplied, plus or minus, to the whole system, if you add it all up, is the sum of dq naught at the temperature T naught, which is equal to T naught times the sum of dq over T. And Kelvin's statement of the second law requires that for net work done that only takes heat from a single source, namely T naught, that's impossible unless you don't supply heat at T naught, you reject heat at T naught. And so in general, for an arbitrary cycle, the sum of dq over T is less than naught, and it's only exactly equal to naught if it's a reversible cycle. All right. So that's a very important result. Right. Now, I'm going to prove the next thing to you. We're getting very close to the idea of entropy. Since the integral around an arbitrary reversible cycle, dq reversible divided by T equals naught, then it is true that the integral from A up to B of dq reversible divided by T is independent of the path for a reversible process. Now that is, you'd say, I don't believe that. Well, I'm going to prove it for you right now. Let's look at it. So here's the proof. You could easily not believe it. And I wouldn't be surprised if I actually asked you whether you really believed it. You'd say you haven't got a clue. So I'm going to prove it for you. So here's my circle. That's this arbitrary cycle in a PV diagram. And I'm going to start at A, and I'm going to go to B. And I've got two paths here to go around this loop. I can go from A to B and then back on 3. So that's path 1 and path 3. Or I can go from A to B on path 2 and back on path 3. Clear? Right. So what this reversible cycle says that the integral from A to B on path 1 plus the integral from A to B on path 3, that has to be, we've just proven, equal to 0. But it's also equal to the integral from A to B on 2 plus the integral from B to A on 3. They're both 0. So you can see that I can cancel this right-hand side from B to A on 3. I can cancel it on the right-hand side and on the left-hand side, and I'm left with the idea that the integral from A to B on 1 is exactly equal to the integral from A to B on 2. It's independent of the path. It only depends on the state A and B. So the integral from A to B of dq reversible divided by T is independent of the path. And that is the basis of the entropy. Let's see why. Let's see why. All right, so going back to that first figure I had, the integral from A to B on 1 plus the integral from B to A on 2. So let's look at that again. Oh, good God. You'd have thought this was easy, wouldn't you? You could say that I don't know what I'm doing. We've done all of that. And we've done that. And we were here. So what I just said was that I just said that the integral from a to b plus the integral from b to a, let's just look at that, from a to b and b to a. So that's on the top two curves that I had. So here was 1, and here was 2, and here was a, and here was b. So the integral from a to b on 2, so if I go around this way, and then the first line is from a to b on 1, plus the integral from, and that's plus the integral from b to a back again, and that's around a loop, and so that must be exactly 0. And so I proved to you that the integral from a to b on 1 was also the integral from a to b on 2, so I've replaced that. And so the integral from a to b on 2 plus the integral from b to a on 2 is equal to 0, and it's obvious because it's the same path. And so the integral from a to b must be minus the integral from b to a. That must be true. All right, so now what can we say? But the integral from a to b on 3 could be made up of an integral from a to some other place 0, and then from 0 up to b, because it only depends on a and b and not on the path. We've just proven that. So the integral from a to 0 plus the integral from 0 to b is the integral from a to b. And so that's equal to the integral from 0 to b, and the integral from a to 0, I've just shown you, is minus the integral from 0 to a. So this is the integral from 0 to b minus the integral from 0 to a. And that is another remarkable fact when you think about it, because it enables you to define the entropy SA as the integral from 0 up to a of dq reversible divided by t. So then for fixed O, SA can depend only on the state A, since the integral from 0 to a doesn't depend on the path, and I've just proven that. Yes, since the integral from 0 to a is independent of the path for a reversible process. SA is the entropy at state A. A different reference point, if I'd started with a different reference point and not integrated from 0 up to a, but started at 0 prime up to a, then if I'd used a different reference point, that would lead to SA being different from SA prime, but only by a constant. And the constant would be the integral from 0 up to 0 prime of dq reversible divided by t. That's a constant. So I can choose, I have to be systematic, I have to choose 0 somewhere, but it won't matter what I use, so long as I'm talking about differences in entropy, then these constants will all disappear. So the integral from a to b of dq reversible divided by t is SB minus SA, irrespective of the reference point, irrespective. And you can see that that's telling you that SB and SA depend only on the state A and B And so entropy is a variable of state, like the volume and the pressure and the temperature. And you find it by integrating from some reference point up to the point you're interested in, by choosing a process